The titration of a weak base with a strong acid is very similar in look, in calculation, and in concept to a weak acid with a strong base. So this time our pH starts high, but it's not quite as high as if the base were strong because it's not ionized as much. It doesn't have as much hydroxide. We would have a little bit of pH drop, but once again, we've got a fairly flat region where the pH isn't really changing by more than 2. That is near or around our half equivalence point. The pH at the half equivalence point is equal to the pKa of the base. Sometimes this is a little bit confusing, but remember that Ka is the thing that makes the connection to hydrogen ion. So it's always the pKa is equal to the pH at the half equivalence point, whether we're looking at acids with bases, bases with acids, or which thing is weak. That's a common question, both in free response and in multiple choice, that sometimes seems a little bit trickier when we are starting with a weak base. When we're at that half equivalence point, the same idea has happened. Initially, we have only weak base in solution. When we get to the equivalence point, all of our weak base has reacted away. It's at the half equivalence point that we still have some of our base, half of it hasn't reacted, but half of it has. And in reacting, it has turned into its conjugate acid. So the half equivalence point, once again, is very important in terms of pH, pKa, also knowing we have an equal amount of the two. Anything before the half equivalence point, we have more base than conjugate acid. Anything after the half equivalence point, we have more conjugate acid than weak base. Those are good conceptual questions you can be asked about. Here it says rise, and I'm going to change that as we work to drop. So big drop in pH, it's another steep one. We have a inflection point once again as we become neutralized. The equivalence point is below 7 because, as we just said, we are making a conjugate acid. Anything past here, we have more conjugate acid than weak base. And at the equivalence point, we don't have any base left. It has all turned into our conjugate acid. So in terms of what's floating around in solution, all of the HCl has been neutralized. All of the weak base has been neutralized. We've made water and then a conjugate acid. That conjugate acid donates its hydrogen to the water, turning back into a small amount of our base, but more importantly, producing that hydrogen ion. So that is why our pH is below 7, because we've made more hydrogen ion. Then once we get down here, we'll see our pH end very low because we have an excess of strong acid. We just need to know the total moles of hydrogen ion over our total volume to find that pH. So in terms of concept, we would have the same sort of mix of stoichiometry for some things when we're thinking about the acid reacting with the base, to think about limiting an excess and number of moles and total volume and molarity, and equilibrium. The initial situation's equilibrium, the equivalence point after we've done our stoichiometry is equilibrium, and anytime we're trying to figure out the amount of an ion in solution up to and including the equivalence point, there's some equilibrium involved using our Kb until we get to our equivalence point, then it would be our Ka because it is the weak acid version, the conjugate acid that's in solution. With these, you do need to pay attention to, if you're solving for Kb, your X is equal to hydroxide. When you're solving for Ka or with Ka, your X is your hydrogen ion. But the same things are true about the relationships between hydrogen and hydroxide ions with Kw, with Ka and Kb, using Kw, and then also knowing if you know your pH, that can tell you your hydrogen, which can connect to your hydroxide. So we've got a problem here that's using a lot of the same ideas, but also ends with a really good conceptual idea where we don't have to do the math, but just understanding in terms of a titration, what we know about the species we start with, which in this case would be our weak base, and how much of it has turned into our weak conjugate acid. This is a very common comparison in both multiple choice and free response, and shows that you understand the relationship or what's happening during a titration without just doing calculations.